Hello, my name is Steve Mazur. I'm an aerospace engineer. I'm going to be entering my junior year in the fall. I've been working with Andy Ridgway under the advisement of Dr. John Shaw on something called shape memory polymers. Quick overview, what is a shape memory polymer? What is possible uses? And I'll show you guys a demo. All plastics have something that's called a glass transition temperature. Below this temperature, they are rigid and stiff. Above it, they are soft and rubbery. The shape memory polymers have a special characteristic. If you raise a shape memory polymer above its glass transition temperature and then deform it while holding that force, deformation force, and cool it back down below its glass transition temperature, it will keep that shape. It will freeze in that form. If you then remove the deformation force and raise it back above its glass transition temperature, it will remember its shape and go back to where it was before. It can recover up to strains up to 150 or 200%. Some possible uses of this material are biomedical. It can be engineered so that it's biodegradable. They're talking about using it in car fenders, so if you got a dent, you could just get out a hairdryer and heat it up and it would go back to where it was. Also, in aerospace, they're researching currently on making a morphing wing structure. I've got a video for you guys. Right now I'm heating up a sample with a heat gun to above its glass transition temperature and deforming it by twisting it around on itself. It's air cooling right now. It's going below its glass transition temperature. Now as you can see, it's stiff and rigid. We're freezing the shape that I deformed it to. Now, since there's no force on it, and it's heating back above its glass transition temperature, it uncurls and goes back to the way it was. What have I been doing with this? I'm doing experimentation first with a dynamic mechanical analyzer to find the glass transition temperature. Basically, I did 3-point bending test over a range of temperatures, and I found the drastic change in stiffness is where the glass transition temperature is. Next, we used an Instron tensile tester to pull on dog bone specimens of this plastic and studied various stress and strain curves that we got from this data. Lastly, we have been setting up a membrane experiment to study a three-dimensional stress and strain. These pictures show that membrane setup. Basically, you have a circular sample of plastic over the end of a pipe, and then from below you inflate the specimen with silicone oil, and so we're reading pressure and volume at all times, and the silicone oil is there to for temperature control. We have cartridge heaters inside there that heat the silicone, and there's a thermal chamber not shown that goes over the setup on the right, which is the zoomed in view. Basically, this lets us know what the three-dimensional stress and strain of the sample are by viewing the dots aligned in a matrix on the sample. It's difficult to see in this picture, but we take pictures as with the 4 cameras shown on the left. As the experiment progresses, we can, from the change in location of these dots, we can tell where the stress and strain at each point. Lastly, we wanted to get some design work, so we've been designing a shape memory alloy catapult. This uses the alloy, not the polymer. The difference here is that you stretch out the wire to 105% of its original length, and then it recovers 5% of the length when it actuates. It actuates the same way by heating up. We heat it up through resistive heating. We just send a current through it. Basically, the wire is anchored to the board as shown on the left, and then it's wrapped around a pulley affixed to a shaft, which is fixed to the lever arm, as shown on the right. So when it actuates, it will fling the lever arm. And this is going to be used in a demonstration in September to show people the power of shape memory alloys. Lastly, some plans and final thoughts. I'm planning on going to grad school to get my 5-year master's from the university. And after that, I'm not really sure. We'll have to see when I get there. What I've learned from SURE is basically how experimentation and research work. It's a lot different than the classroom. Like, something may look good on paper, but it's more difficult to do in actuality. And so tips for future SURE students: don't give up. It's going to be difficult at times and very frustrating, but it's worth it in the end. And the experience is what you make it, so give it your all.